Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The solar system, our cosmic neighborhood, is a realm of astonishing diversity and extremes. From the searing heat of Mercury, scorched by the sun's relentless rays, to the frozen expanse of distant Neptune, this celestial neighborhood is home to some of the most hostile, mysterious, and awe-inspiring environments imaginable. Exploring these extremes helps us understand not only the planets and moons themselves, but also the fundamental forces and processes that govern the universe. Each world, each celestial body, presents a unique set of challenges, dangers, and wonders, painting a picture of a solar system that is as perilous as it is beautiful. Close to the sun, Mercury stands as a monument to extremes. With virtually no atmosphere to buffer its surface, temperatures swing from blistering heat during the day to frigid cold at night. Daytime temperatures soar above 400 degrees Celsius, capable of melting lead, while nights plunge below -180 degrees Celsius. The planet's surface is a cratered, desolate landscape, bearing witness to billions of years of impacts from asteroids and comets. Mercury's proximity to the sun also exposes it to intense solar radiation and a constant bombardment of charged particles. It is a world where survival, even for robotic explorers, is a matter of carefully engineered shielding and timing, a place where the extremes of heat and cold coexist in a delicate, unforgiving balance. Not far from Mercury lies Venus, a planet often called Earth's twin because of its similar size and composition, yet it is a twin in name only. Venus's thick, toxic atmosphere is dominated by carbon dioxide, trapping heat in a runaway greenhouse effect that makes it the hottest planet in the solar system. Surface temperatures soar past 460 degrees Celsius, hot enough to melt lead and destroy most spacecraft within hours. Acidic clouds composed of sulfuric acid rain down upon the surface, corroding everything in their path. The pressure at Venus's surface is crushing, equivalent to the weight of hundreds of Earth atmospheres stacked upon a single square meter. Winds whip across its upper atmosphere at speeds over 300 kilometers per hour, stirring its dense clouds into patterns that shift and swirl with terrifying energy. Venus is a reminder that what seems familiar can be utterly alien when extremes are at play, a planet of beauty hidden beneath a veil of deadly conditions. Moving outward, the gas giants, Jupiter and Saturn, introduce extremes of violence, gravity, and atmospheric violence. Jupiter, the behemoth of the solar system, is more than twice as massive as all other planets combined. Its gravity is so strong that it shapes the orbits of nearby asteroids and even influences the paths of comets. Jupiter's atmosphere is a turbulent storm of hydrogen and helium, marked by violent winds, immense pressure, and raging storms like the Great Red Spot, a hurricane larger than Earth that has persisted for centuries. Within its depths, pressures and temperatures rise to levels far beyond anything experienced on our planet, creating conditions where hydrogen may exist in a metallic state, conducting electricity and generating Jupiter's powerful magnetic field. This magnetic field, one of the strongest in the solar system, traps charged particles, creating radiation belts that would be lethal to any unshielded spacecraft or human visitor. Saturn, though famous for its magnificent rings, is equally extreme in its own ways. Its rings, composed of billions of icy particles ranging from dust-sized grains to mountains, orbit in a delicate dance governed by gravity and collisions. Saturn's atmosphere, like Jupiter's, is a stormy realm with winds reaching speeds of over 1,800 kilometers per hour near the equator. Within its gaseous envelope, immense pressures and temperatures create conditions that challenge our understanding of matter. The planet emits more heat than it receives from the sun, a mysterious phenomenon that hints at complex processes deep within its core. Saturn's moons too harbor extremes. Titan, shrouded in a dense, nitrogen-rich atmosphere, hosts lakes of liquid methane and ethane, a frigid landscape where temperatures drop below -180 degrees Celsius. Meanwhile, Enceladus hides a subsurface ocean beneath its icy crust, geysers of water vapor and organic compounds jetting into space, hinting at conditions that may be suitable for life, albeit in a harsh, alien environment. Further from the Sun, Uranus and Neptune extend the range of extremes to the icy giants. Uranus, tilted almost entirely on its side, experiences seasons that last decades, with one pole bathed in continuous sunlight, while the other remains in darkness for decades at a time. Its atmosphere, composed mainly of hydrogen, helium, and methane, gives it a striking blue-green hue, and it harbors powerful winds and storms that circulate around the planet at incredible speeds. Neptune, the most distant of the giant planets, is a realm of supersonic winds, with storms that dwarf anything on Earth and temperatures that plunge to hundreds of degrees below zero. The planet's moon Triton is equally extreme, with geysers of nitrogen gas and a retrograde orbit, suggesting it was captured from the Kuiper Belt, a relic of the solar system's distant frontier. The smaller bodies of the solar system, though often overlooked, are also hosts to extremes. The asteroid belt, a region between Mars and Jupiter, is home to countless rocky fragments that endure high-speed collisions and intense radiation. Some asteroids, like Vesta and Ceres, are remnants of planetesimals, bodies that failed to form into full-fledged planets, offering clues to the early solar system. The Kuiper Belt and the distant Oort cloud take these extremes to their limits. Objects in these frozen regions are trapped in frigid darkness, exposed to cosmic radiation and temperatures near absolute zero, untouched for billions of years. These icy bodies, including dwarf planets like Pluto, Makemake, and Eris, are frozen time capsules that hold secrets of the solar system's formation and evolution. Even the Sun, the very center of our planetary system, represents an extreme that shapes all else. Its immense gravitational pull anchors the planets in their orbits, while its nuclear furnace emits energy across the electromagnetic spectrum, driving weather, climates, and magnetic fields on every world. Solar flares and coronal mass ejections hurl charged particles into space, producing spectacular auroras on planets like Earth and posing hazards for spacecraft. The Sun's energy is both life-giving and destructive, a duality that underscores the fine balance required to sustain life in the solar system. Beyond physical extremes, the solar system exhibits extremes of motion and time. Some moons, like Jupiter's Io, experience intense tidal heating due to gravitational interactions, resulting in hundreds of active volcanoes that continuously reshape its surface. Mercury's slow rotation, coupled with its elliptical orbit, produces unusual day-night cycles, while Venus's retrograde spin makes its day longer than its year. In the outer reaches, objects take centuries or millennia to complete a single orbit around the Sun, moving in icy solitude through the void. These extremes of motion illustrate the intricate gravitational dance that governs all celestial bodies, a choreography that can produce both serene orbital patterns and violent collisions. The solar system's extremes are not limited to danger and hostility. They also offer opportunities for discovery and wonder. Volcanic activity on moons like Io and Enceladus provides natural laboratories to study geophysical processes. The rings of Saturn, constantly shifting and evolving, reveal the dynamics of particle physics and gravitational interactions. High radiation environments like Jupiter's magnetosphere challenge engineers to design resilient spacecraft, pushing the boundaries of technology. Even the frozen edges of the Kuiper Belt and Oort cloud, distant and desolate, are frontiers for understanding the origins of the solar system and the potential for life beyond Earth. Each extreme environment, while inhospitable, expands the limits of our knowledge and inspires the imagination. Human exploration of these extremes remains a formidable challenge. Robotic missions have braved Venus's crushing atmosphere, penetrated Jupiter's radiation belts, and skimmed past icy comets at thousands of kilometers per hour. The technology developed for these missions, from heat-resistant materials to autonomous navigation systems, represents the cutting edge of human ingenuity. Future missions may push further, returning samples from distant asteroids, exploring the subsurface oceans of Europa and Enceladus, or even sending probes into the Sun's corona. These endeavors not only expand our scientific understanding, but also test the limits of what humans and our machines can endure. The extremes of the solar system also serve as a mirror, reflecting conditions that challenge our understanding of physics, chemistry, and planetary science. They prompt questions about planetary formation, the potential for life in harsh environments, and the long-term evolution of planetary atmospheres and surfaces. Studying extreme environments in our own celestial backyard prepares us to recognize and interpret similar conditions on exoplanets around distant stars. The lessons learned from extremes here guide the search for life and habitability across the galaxy, informing our quest to answer one of humanity's most profound questions. Are we alone? From the furnace of Mercury to the frozen void of the Oort cloud, the solar system is a theater of extremes, each stage presenting its own drama and mystery. Every planet, moon, asteroid, and comet offers a unique story of survival, transformation, and resilience under conditions that defy earthly norms. The extremes are a reminder of the power of nature, the influence of gravity, the energy of the sun, and the relentless passage of time. They are also a testament to human curiosity and determination as we strive to understand, explore, and ultimately thrive in a universe that is far vaster and more extreme than we can fully imagine. Among the most extreme worlds in the solar system, Jupiter's moon Io stands out as the most volcanically active body known. Powered by intense tidal forces from Jupiter's massive gravity and the gravitational tugs of its neighboring moons Europa and Ganymede, Io's interior is constantly kneaded and flexed, generating heat that fuels hundreds of active volcanoes. Lava fountains erupt dozens of kilometers into the sky, and vast fields of sulfur and sulfur dioxide frost coat the surface in bright yellow, red, and white hues. The surface reshapes itself continuously, erasing impact craters within decades, creating a young, ever-changing landscape. The volcanic plumes spew material into space, contributing to a thin atmosphere around Io and even to Jupiter's own magnetosphere, demonstrating how extreme geological activity on a small moon can influence a giant planet. For scientists, Io is a natural laboratory for studying tidal heating, volcanic chemistry, and the mechanics of planetary interiors under extreme stress. Meanwhile, Europa, another of Jupiter's Galilean moons, presents a different kind of extreme. Beneath its fractured, icy crust lies a global ocean of liquid water, kept warm by tidal heating. The ice surface is riddled with cracks and ridges, evidence of a restless world constantly shifting and flexing. This hidden ocean, potentially in contact with the rocky seafloor, may harbor conditions suitable for life, even in a place so far from the warmth of the sun. Europa's extreme environment challenges our ideas about habitability, showing that life could exist in worlds with no sunlight, under kilometers of ice, where pressures are immense and temperatures just below freezing. Robotic missions are being designed to probe this icy world, using ice-penetrating radar, spectrometers, and even landers that could sample surface ice and possibly plumes venting from below. The extremes of Europa, its hidden ocean, surface fractures, and radiation-bathed environment make it a tantalizing target in the search for life beyond Earth. Saturn's moon Enceladus offers a similarly compelling extreme. Despite its small size, Enceladus maintains a subsurface ocean that vents through fractures in its icy crust, forming geysers that shoot water vapor, ice grains, and organic compounds into space. These jets feed Saturn's E-ring, linking the moon's activity directly to the planet's ring system. The energy required to sustain these plumes comes from tidal interactions with Saturn, making Enceladus a dynamic world in the cold reaches of the solar system. Surface temperatures are extreme, plunging to near -200 degrees Celsius, and yet beneath the ice lies a liquid ocean, heated and potentially habitable. The presence of organic molecules, along with water and energy, makes Enceladus a key focus for astrobiologists, representing a tiny yet extreme oasis of potential life. Moving back to the inner solar system, Mars presents extremes of a different nature. Though less hostile than Venus or Mercury in temperature and pressure, Mars is a world of intense winds, dust storms, and massive canyons and volcanoes. The planet's surface experiences temperature swings from -120 degrees Celsius at night to 20 degrees during the day near the equator. Its atmosphere, thin and primarily carbon dioxide, offers little protection from solar radiation, making the surface a dangerous place for unshielded humans or electronics. Mars hosts Olympus Mons, the tallest volcano in the solar system, nearly 3 times the height of Mount Everest, and Valle Marineris, a canyon system that would stretch across the United States, emphasizing geological extremes unmatched on Earth. Dust storms can engulf the entire planet, reducing visibility to near zero and affecting surface conditions for weeks, demonstrating the extremes of climate on a planet shaped by both its atmosphere and its position in the solar system. Venus, though discussed earlier, reveals further extremes when we consider its high-speed winds in the upper atmosphere, which circulate around the planet in just 4 Earth days despite the slow rotation of the surface. This phenomenon, known as superrotation, creates extreme shear between layers of atmosphere, generating massive waves and turbulence that are still not fully understood. Below the cloud layer, pressures crush spacecraft designed to explore the surface, exemplifying extremes not just of temperature, but of mechanical force. Venus's combination of heat, pressure, and corrosive chemistry makes it a world unmatched in its hostility, a place where only specially designed probes have dared to survive, even for a short time. The asteroid belt, located between Mars and Jupiter, is a region of extremes on a different scale. Asteroids range from tiny rubble piles just a few meters across to massive bodies like Ceres and Vesta, which are nearly planetary in size. These rocks orbit at high speeds, occasionally colliding in explosive impacts that shape their surfaces and create smaller fragments. Some asteroids, such as the metallic M-type or carbonaceous C-type, are remnants of the early solar system, preserving clues about planetary formation. Spacecraft missions, Dawn and CASREX, have explored these bodies, revealing craters, grooves, and even signs of past geological activity. The extreme variability in composition, size, and surface conditions in the asteroid belt makes it a treasure trove for understanding the solar system's formative years and the violent processes that still occur in this chaotic zone. Beyond the main planets and asteroid belt, the icy frontier of the solar system pushes extremes to their limit. The Kuiper Belt, home to Pluto, Haumea, Makemake, and countless smaller icy bodies, extends far beyond Neptune, where sunlight is weak and temperatures hover just above absolute zero. Objects in this region are frozen relics, preserving ices of methane, nitrogen, and water that date back to the birth of the solar system. Pluto itself exhibits extreme geography, vast nitrogen ice plains, towering mountains of water ice, and glaciers flowing across a frigid landscape, demonstrating geological activity in a place where sunlight is a fraction of Earth's. Even farther out, the hypothetical Oort cloud, a spherical shell of icy bodies surrounding the solar system, represents extremes of isolation, distance, and time. Objects here can take millions of years to orbit the sun, drifting in near-perfect cold and darkness, influenced only by the slightest gravitational tugs from passing stars or galactic tides. Comets, often originating from the Kuiper Belt or Oort cloud, bring their own brand of extremes when they approach the inner solar system. Traveling at tens of kilometers per second, comets heat rapidly under the sun's rays, causing sublimation of ices and the formation of luminous tails that stretch millions of kilometers. The outgassing produces jets that can alter the comet's rotation and trajectory, demonstrating the violent dynamics of seemingly small bodies. The nucleus of a comet is fragile, porous, and irregular, yet it survives these extremes of heat, radiation, and solar wind long enough to provide spectacular celestial displays. Cometary impacts in the past have delivered water, organics, and possibly even precursors to life to Earth, illustrating how extreme events can also be crucial for planetary evolution. Even the farthest reaches of the solar system are not uniform in their extremes. The heliosphere, the vast bubble of charged particles emitted by the sun, extends well beyond Pluto, forming a protective shield against cosmic rays. The boundary of this sphere, the heliopause, marks the transition to interstellar space, where particles and radiation from the galaxy itself dominate. Spacecraft such as Voyager 1 and Voyager 2 have ventured into this realm, experiencing conditions unlike anywhere else in the solar system: low particle densities, magnetic turbulence, and the edge of solar influence. The extremes of space are not merely temperature or pressure. They include radiation, vacuum, and the very absence of matter, challenging our understanding of what it means to traverse a cosmic environment. The moons of Saturn provide additional examples of extremes. Titan, with its thick nitrogen-rich atmosphere, hosts methane rivers, lakes, and rain, forming an alien hydrological cycle that mirrors Earth's water cycle, but with entirely different chemicals and temperatures around -180 degrees Fahrenheit degrees Celsius. The combination of dense atmosphere, hydrocarbon seas, and frigid temperatures creates extreme weather patterns, with winds, storms, and dunes shaped by processes familiar yet profoundly alien. These conditions make Titan one of the most Earth-like yet extreme places in the solar system, where explorers must contend with cold, chemistry, and a surface that is both solid and fluid in unexpected ways. Neptune, the outermost of the giant planets, is a realm of supersonic winds and extreme storms. Despite being nearly 30 times farther from the Sun than Earth, Neptune's atmosphere is dynamic and violent. Winds on this icy giant reach speeds exceeding 2,100 kilometers per hour, faster than a commercial jet flies in hours. Storms, some larger than Earth itself, appear as dark spots in the planet's blue atmosphere, swirling with tremendous energy and occasionally disappearing or reforming in short periods. The cause of Neptune's intense atmospheric motion remains partly a mystery, as the planet receives only a tiny fraction of the Sun's energy compared to Earth. Internal heat from the planet's core likely drives these ferocious storms, illustrating how energy can produce extremes even at the edges of the solar system. Neptune's moon Triton adds another layer of extremity. With a retrograde orbit and cryovolcanic activity, Triton spews nitrogen gas and geysers that rise tens of kilometers above the surface. Its frigid environment, with temperatures around -235 degrees Celsius, makes it one of the coldest known objects in the solar system. Yet dynamic forces reshape its surface over time. Pluto, though no longer classified as a major planet, embodies extremes in its own right. Its surface is a mosaic of nitrogen ice plains, towering mountains made of water ice, and glaciers that slowly creep across the dwarf planet. Seasonal changes, driven by its highly elliptical orbit, cause parts of Pluto's surface to sublimate into atmosphere when closer to the Sun, only to refreeze when it recedes to the outer reaches of its orbit. This cycle produces variations in surface pressure and temperature, creating an environment of extremes that challenge any conventional definition of habitability. Pluto's largest moon, Charon, presents yet another extreme with its massive canyon system, including Serenity Chasma, which stretches more than 1,000 kilometers long and up to 12 kilometers deep, rivaling the largest canyons on Earth. Together, Pluto and Charon offer insights into how small, distant worlds can harbor dramatic geological and atmospheric phenomena, even in near-perpetual cold. Asteroids and comets traveling through the solar system often experience extremes of speed and impact. Some near-Earth asteroids whiz past our planet at tens of kilometers per second, moving so fast that even tiny collisions could release energy equivalent to nuclear explosions. Comets, on the other hand, undergo intense thermal stress as they approach the Sun. Sublimation of ices leads to explosive jets and erosion of their surfaces, altering their rotation and even fragmenting some into multiple pieces. The famous comet Shoemaker-Levy 9, for example, collided with Jupiter in 1994, producing visible scars in the planet's atmosphere and releasing energy millions of times greater than Earth's largest nuclear bombs. These extreme interactions underscore the dynamic, sometimes violent, nature of the solar system, where even small bodies can have enormous consequences when physics, gravity, and speed combine. Solar radiation itself represents an extreme pervasive throughout the solar system. The Sun emits a continuous stream of charged particles known as the solar wind, which can shape planetary magnetospheres, strip atmospheres, and produce spectacular auroras. Mercury, for instance, lacks a substantial atmosphere, so its surface is directly bombarded by these energetic particles, producing space weathering that alters the regolith and contributes to extreme surface conditions. Jupiter's magnetosphere traps vast numbers of charged particles, creating radiation belts so intense that they would be fatal to unshielded humans in moments. Even Earth's magnetic field, though protective, channels solar wind particles to the poles, producing extreme displays of light, but also demonstrating the immense power of these interactions. In the outer solar system, where sunlight is weak, these charged particles still permeate space, influencing icy surfaces and shaping the chemistry of distant bodies, proving that extremes are not solely about heat or cold, but also about radiation and energy. Saturn's rings are another testament to extreme processes. Though visually serene from a distance, they are in a constant state of motion and collision. Billions of icy particles, ranging from minuscule grains to mountain-sized chunks, orbit the planet, colliding and bouncing in a delicate balance dictated by gravity. Some moons, like Pandora and Prometheus, act as shepherds, sculpting ring edges and creating gaps, while meteoroid impacts stir the rings with waves and wakes. Saturn's rings are ancient yet dynamic, fragile yet vast, representing extremes of scale, motion, and stability. Studying them reveals insights into orbital mechanics, particle interactions, and the potential origins of planetary ring systems around other stars. Extreme temperature variations occur throughout the solar system, each world showcasing unique patterns. Mercury's slow rotation, combined with its proximity to the sun, produces days that are scorching hot, while nights are bitterly cold, exemplifying extremes of thermal stress. Europa and Enceladus, though frigid on the surface, harbor subsurface oceans that are warm enough to remain liquid, demonstrating extremes of temperature layered within a single celestial body. Mars, with its thin atmosphere, experiences rapid heating and cooling, while Venus maintains a near-uniform extreme heat due to its dense atmosphere and greenhouse effect. These variations highlight that extremes are relative and layered, encompassing not only absolute values of temperature but also gradients and contrasts that shape surface and atmospheric conditions. The solar system also presents extremes in gravity. Jupiter's immense mass produces gravitational forces that dominate the inner solar system, influencing asteroid paths, shaping satellite orbits, and even creating tidal heating in moons like Io. On Earth, gravity is a constant, familiar force, but on small bodies like asteroids, gravity can be almost negligible, allowing dust and boulders to float with minimal restraint. The dwarf planet Ceres, though relatively small, has sufficient gravity to retain a thin atmosphere and support cryovolcanic activity, demonstrating the delicate balance between size, mass, and the effects of gravity. These extremes influence not only movement in orbit, but also geological processes and the potential for maintaining atmospheres or oceans. Radiation, another extreme factor, varies dramatically across the solar system. Venus's dense atmosphere protects its surface from cosmic rays, but temperatures and pressure remain lethal. Mars's thin atmosphere provides little shielding, exposing the surface to intense ultraviolet and cosmic radiation. Jupiter and Saturn generate magnetospheres that trap charged particles, creating deadly radiation belts. Even in the distant Kuiper Belt, cosmic rays slowly alter icy surfaces over billions of years, producing chemical changes that record the history of the solar system. Radiation shapes surfaces, chemistry, and potential habitability, illustrating that extremes are not limited to temperature, pressure, or gravity alone. Comets and icy bodies experience extreme seasonal cycles and orbital eccentricities. Halley's Comet, for example, travels from beyond Neptune to the inner solar system in a highly elliptical orbit, exposing it to extremes of sunlight and darkness, heat and cold. The intense solar heating near perihelion causes rapid outgassing, while in the distant reaches of its orbit, the comet becomes a frozen relic of primordial materials. These extreme cycles not only sculpt the physical structure of comets, but also provide scientists with a window into the processes that shaped the solar system billions of years ago. Jupiter's magnetosphere is another unparalleled extreme. It is the largest structure in the solar system, aside from the sun itself, extending millions of kilometers into space. Within it, charged particles are trapped and accelerated to tremendous energies, creating radiation belts so intense that spacecraft must be heavily shielded to survive even brief passes. These radiation belts sculpt the surfaces of moons like Europa and Io, sputtering particles and altering chemical compositions over time. The interaction of the magnetosphere with the solar wind generates auroras far brighter and more energetic than those on Earth, visible as spectacular light shows around the planet's poles. The scale and intensity of Jupiter's magnetic environment are extreme in ways that challenge our understanding of planetary physics, demonstrating that magnetism can dominate not only local space, but also planetary evolution. Saturn's magnetic field, though weaker than Jupiter's, also creates extreme space weather. Its magnetic field traps plasma and charged particles, interacting with its rings and moons in complex ways. Some of Saturn's moons, like Enceladus, experience the consequences of this magnetic environment directly, as ejected particles from geysers are caught and swept along magnetic field lines. Saturn's rings themselves are influenced by electromagnetic forces as tiny ice grains interact with the planet's magnetic field and charged particles from the sun. The subtle interplay of gravity, electromagnetism, and particle collisions creates a system of extremes where nothing remains static, highlighting the dynamic nature of Saturn's environment. Extreme impacts have left their mark across the solar system, from Mercury to distant icy bodies. Large craters and basins on the Moon, Mercury, Mars, and Ceres bear witness to the violent history of collisions with asteroids and comets. Some of these impacts release energy comparable to millions of nuclear explosions, reshaping landscapes in seconds. On Mars, the Hellas Basin spans thousands of kilometers, and on Mercury, the Perilous Basin is one of the largest impact structures known, demonstrating the sheer scale of celestial violence. Even small bodies like asteroids or comet fragments can produce localized destruction, and in the early solar system, such impacts likely played a role in delivering water and organic molecules to Earth, paradoxically supporting life through extreme events. The chemistry of extreme environments is also fascinating. On Venus, the atmosphere's sulfuric acid clouds create corrosive rain, a chemical extreme that destroys metals and spacecraft coatings within hours. On Titan, the hydrocarbon lakes and rivers host chemical processes at temperatures far below Earth's, forming methane and ethane-based precipitation and erosion. Europa and Enceladus, beneath their icy shells, may harbor water-rock interactions that produce complex organic molecules, hinting at the potential for prebiotic chemistry in conditions very different from those on Earth. Even the outer Kuiper belt and Oort cloud contain pristine ices and organics, preserved for billions of years, providing a chemical record of the early solar system in extreme cold and isolation. Extreme pressures exist not only in planetary interiors, but also in ice-covered oceans. Europa and Enceladus's subsurface oceans are under kilometers of ice, producing immense pressures that may reach hundreds of times Earth's surface pressure. Such extremes influence the behavior of water and dissolve chemicals, potentially allowing for life to exist in forms adapted to crushing pressures. The combination of pressure, temperature, chemical composition, and energy from tidal heating creates conditions unlike any on Earth, demonstrating that life could exist in realms once considered uninhabitable. Even the concept of time reaches extremes in the solar system. Objects in the distant Oort cloud may take millions of years to complete a single orbit around the sun. Tidal locking, where a moon orbits so that one side always faces its planet, creates eternal day and night on moons such as the Moon, Ganymede, and Titan, producing extreme cycles of light and dark. Venus's slow retrograde rotation results in a day longer than its year, creating an environment where solar heating is prolonged and uniform across the surface, adding yet another layer of extremity to planetary conditions. Human exploration must confront all of these extremes. Robotic missions have proven capable of surviving Venus's heat for short periods, landing on Mercury, diving into Saturn's rings vicinity, and even exploring the icy realms of the outer solar system. Future missions aim to drill through Europa's ice, fly through Enceladus's geysers, and even land on Titan's hydrocarbon lakes. Each of these endeavors requires technology capable of withstanding extremes of temperature, pressure, radiation, and chemical corrosion. Understanding these extremes not only expands our knowledge, but also tests the limits of engineering and imagination. The solar system's extremes are more than scientific curiosities. They are windows into universal processes. They teach us about planetary formation, orbital dynamics, and chemical evolution, and the potential for life in conditions radically different from Earth. Every extreme environment, from volcanic Io to icy Triton, from scorching Venus to frozen Pluto, tells a story about the forces that have shaped our cosmic neighborhood over billions of years. They remind us that the universe is not uniform, not gentle, but rather a place of extraordinary diversity and power, where beauty and danger coexist in forms we are only beginning to comprehend. These extremes, when considered together, reveal a solar system that is dynamic, violent, delicate, and beautiful. The interplay of gravity, radiation, temperature, pressure, chemistry, and time creates a web of forces that shape each world uniquely. From the surface of Mercury, seared by the sun, to the icy depths of Europa and Enceladus, from Jupiter's magnetic fury to the serene yet frigid plains of Pluto, the solar system is a laboratory of extremes. Each extreme challenges our assumptions, expands the boundaries of what is possible, and inspires the human spirit to explore further. Ultimately, understanding the solar system's most extreme places enriches our appreciation for the fragility and resilience of life on Earth. It shows us the diversity of planetary environments and the range of conditions under which matter behaves and evolves. It sparks our imagination, driving curiosity, exploration, and the desire to venture into the unknown. In studying extremes, we learn not only about other worlds, but also about the delicate balance that allows life to flourish on our own, highlighting the extraordinary nature of our home in a universe defined by extremes. Uranus presents some of the most unusual extremes in the solar system. Unlike any other planet, it rotates on its side with an axial tilt of about 98 degrees. This extreme tilt creates a bizarre seasonal pattern. Each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. The tilt affects atmospheric circulation, producing unusual wind patterns and storm systems. Uranus's magnetic field is also highly tilted relative to its rotation axis and offset from the planet's center, creating extreme variations in magnetic influence across its surface and moons. These conditions produce a planetary environment that is not only cold, at temperatures around -224 degrees Celsius, but also dynamically extreme, with seasons and magnetic forces unlike any other world in the solar system. Titan, Saturn's largest moon, offers a striking combination of chemical and meteorological extremes. Its dense atmosphere, thicker than Earth's, is mostly nitrogen with traces of methane, producing hydrocarbon rain, lakes, and rivers. The landscape is sculpted by erosion from methane rainfall, wind-driven dunes, and potential cryovolcanism, creating a cycle reminiscent of Earth's water cycle, but in a freezing alien chemistry. Winds sweep across its surface at hundreds of kilometers per hour, while temperatures remain near -179 degrees Celsius. Titan is extreme not only in its cold and chemistry, but also in the sheer unfamiliarity of its environment. A world with lakes of liquid methane and ethane, thick orange clouds, and potentially subsurface water oceans beneath its icy crust. Pluto continues to surprise with extremes in temperature, surface geology, and seasonal cycles. Its nitrogen ice glaciers slowly flow across vast plains, reshaping landscapes over decades. Seasonal sublimation and deposition of nitrogen frost create atmospheric pressure swings and surface changes, while mountains of water ice rise kilometers above frozen plains. Pluto's rotation period of about 6.4 Earth days, combined with its elliptical orbit, produces dramatic variations in sunlight and temperature, revealing a dynamic, extreme world at the edge of our solar system. The interaction between Pluto and its moon Charon, locked in a gravitational dance, adds further extremes through tidal forces that slightly influence surface activity and orbital stability. Even small bodies like asteroids experience extremes. Some near-Earth asteroids, moving at tens of kilometers per second, experience intense heating during close solar approaches and rapid cooling as they retreat into space. Others are fragments from past collisions, irregularly shaped and tumbling chaotically, with surfaces scarred by micrometeoroid impacts and cosmic radiation. Asteroids like Bennu and Ryugu have regolith and boulders that shift with minimal gravity, creating dynamic landscapes under conditions unlike those on any planet. Studying these small bodies exposes the extremes of microgravity, radiation exposure, and collision dynamics. Comets amplify extremes through their dramatic passages near the sun. As frozen time capsules from the solar system's formation, They endure temperatures spanning hundreds of degrees in a single orbit. Sublimation of volatile ices produces glowing comas and tails that stretch millions of kilometers into space, propelled by solar wind. Some comets fragment violently under these stresses, releasing massive amounts of material and energy. Their hypervelocity collisions, whether with planets or other small bodies, demonstrate how extremes of speed, energy, and chemical transformation continue to shape the solar system even today. Observing comets like Halley 67P/Churyumov-Gerasimenko and Shoemaker-Levy 9 provides insight into both past and present extreme processes. Even the void between planets is extreme in its own right. The solar wind, cosmic rays, and interplanetary dust bombard every surface exposed in space. Without protection, surfaces are chemically altered, radiation damage accumulates, and temperatures fluctuate wildly between sunlit and shadowed areas. In the outer solar system, sunlight is nearly 1,000 times weaker than at Earth, yet even this minimal energy interacts with icy surfaces, slowly driving sublimation, migration of volatiles, and the slow reshaping of distant worlds. Space is extreme not only in its emptiness and cold, but also in its quiet, relentless forces acting over billions of years. Looking forward, human exploration of these extreme places will test the boundaries of science and engineering. Concepts such as ice-penetrating probes for Europa, submersibles for Titan's hydrocarbon lakes, landers for Venus's surface, and radiation-hardened spacecraft for Jupiter's magnetosphere illustrate the challenges of surviving extremes. The scientific reward, however, is immense. Understanding extreme geology, chemistry, and potential habitability. Life in the solar system may be constrained to the rare niches where heat, water, and energy coincide, but extreme environments like subsurface oceans or methane lakes expand the possibilities, revealing that even the most hostile worlds may harbor surprising activity or even life. In conclusion, the solar system's extremes stretch our imagination and challenge our understanding. From the scorching, cratered plains of Mercury to the icy geysers of Enceladus, from Venus's crushing, acidic clouds to the supersonic winds of Neptune, each celestial body demonstrates forces and conditions and far beyond those experienced on Earth. They illustrate extremes of temperature, pressure, gravity, radiation, chemical composition, and motion, often layered in ways that create alien, yet fascinating environments. These extreme places are laboratories for studying planetary formation, chemical evolution, atmospheric physics, and the potential for life. They inspire exploration, innovation, and wonder, reminding us that the universe is vast, violent, beautiful, and endlessly surprising. The solar system's most extreme places are not merely curiosities, they are fundamental to understanding our place in the cosmos. They reveal how planets and moons evolve under diverse and hostile conditions, how energy and matter interact in complex ways, and how life might adapt or emerge in environments far removed from Earth's gentle cradle. Exploring extremes challenges humans to invent, adapt, and endure, while expanding knowledge that could one day allow us to reach beyond our solar system. The study of these extremes is a testament to curiosity, resilience, and the human desire to understand the universe. In every extreme environment, from fiery Mercury to frozen Oort cloud objects, we glimpse the dynamic forces that shape worlds and the profound beauty of a solar system defined by extremes.